The megaproject of the future. These 10 projects reveal something important about the future of engineering. The next generation of megaprojects will not be judged simply by the amount of concrete or steel they contain. They will be judged by how intelligently their systems work together. Energy must connect with transportation. Transportation must connect with cities. Cities must connect with digital infrastructure. Water systems must connect with climate resilience. And every one of them must operate within environmental and economic limits. The biggest engineering challenge of the future may therefore not be building something enormous. It may be making something enormous work, reliably, efficiently, sustainably, and for generations. This is the new age of megaproject engineering.
At number 1 is one of the most technically ambitious energy projects ever attempted: China's hydropower development on the lower Yarlung-Zangbo River, often referred to internationally as the Megaproject. Construction officially began in July 2025. The planned system consists of 5 cascading hydropower stations and is expected to generate approximately 300 billion kilowatt-hours of electricity annually. Estimates place the investment above $100 billion, with Reuters reporting a figure of roughly $170 billion. The engineering challenge comes from the geography. The river passes through an enormous canyon system with a dramatic elevation drop. Engineers must work through difficult mountainous terrain while constructing dams, tunnels, underground power facilities and transmission infrastructure. The cascade concept is particularly important. Instead of relying on a single generating structure, multiple hydropower stations can extract energy from different sections of the river system. The water drives turbines. Turbines rotate generators, and generators convert mechanical energy into electricity. But the engineering does not end at the turbines. Hundreds of billions of kilowatt-hours of electricity require an enormous transmission network capable of moving power over long distances. The project also carries serious environmental and geopolitical questions. The Yarlung-Zangbo becomes the Brahmaputra downstream, so changes to water flow, sediment transport, ecosystems and local communities are of major concern to countries including India and Bangladesh. This is what makes the project so significant. It represents the enormous potential of hydropower but also the enormous responsibility that comes with modifying one of Asia's great river systems. If completed as planned, it would redefine the scale of hydroelectric engineering. But its ultimate legacy will depend not only on how much electricity it produces. It will depend on how successfully engineers balance energy, geology, environment, water security and long-term regional consequences. At number 2 is NEOM, one of the world's most ambitious regional development programs. But NEOM must be understood correctly. It is not a single building, and it is not simply one city. It is a vast development region in northwest Saudi Arabia covering approximately 26,500 square kilometers, containing multiple major developments including the Line, Oxagon, Turgina, and other projects. Its technological vision combines renewable energy, advanced manufacturing, artificial intelligence, smart infrastructure, automated transportation, and new approaches to urban design. One of the most important components is Oxagon, positioned as an advanced industrial hub connected to the Red Sea and port of NEOM. The Line represents another approach, dense urban development designed around proximity, connectivity, and reduced dependence on conventional car-based transport. NEOM now describes the Line as advancing through a phased, demand-led approach. But a professional documentary must separate vision from confirmed delivery. The original NEOM concepts have been revised, and reporting in 2026 indicates significant scaling and redesign of parts of the program. That does not make the project less interesting. In fact, it makes the engineering story more realistic. Megaprojects evolve when costs, technology, demand, logistics, and economic conditions change. NEOM is therefore not just an experiment in futuristic architecture. It is an experiment in whether an entire region can be transformed through coordinated infrastructure, energy, industry, technology, and urban planning.
At number 3 is the GCC Railway, a multinational railway system designed to connect the 6 Gulf Cooperation Council countries. The official GCC Railway Authority currently lists a project length of approximately 2,117 kilometers, with passenger trains designed for speeds of up to 200 kilometers per hour and freight trains operating at approximately 80 to 120 kilometers per hour. The project uses European Train Control System Level 2 signaling and targets operation in 2030. The engineering challenge is extraordinary because this is not one country's railway. It is an international infrastructure system. Different countries must coordinate track standards, signaling, border procedures, telecommunications, safety regulations, maintenance and operations. The railway must also survive one of the harshest environments for transportation infrastructure: extreme desert heat, sand, dust and large temperature variations. For high-speed passenger service, track geometry and signaling must be extremely precise. For freight, the system must support heavy loads while maintaining reliability across thousands of kilometers. The economic objective is equally important. A connected railway can reduce dependence on road freight, strengthen regional supply chains, connect ports with industrial centers and increase passenger mobility. This project demonstrates how infrastructure can become a tool for regional economic integration. Instead of 6 separate transportation systems, the goal is one connected Gulf network.
At number 4 is King Abdullah Economic City, or KAEC, a large-scale urban and economic development on Saudi Arabia's Red Sea coast. KAEC is designed around a powerful idea: combine residential districts, logistics, manufacturing, tourism and port infrastructure into one connected economic system. The city covers roughly 185 square kilometers and is anchored by King Abdullah Port and the Industrial Valley. More than 100 multinational and Saudi companies have established operations within the development. From an engineering perspective, the port is particularly important. Modern logistics depend on seamless movement between ships, terminals, roads, railways, warehouses and industrial facilities. That means digital logistics systems, automated cargo handling, advanced cranes, tracking systems and high-capacity transportation networks become as important as concrete and steel. The city also requires enormous utility infrastructure: electricity, water, wastewater treatment, telecommunications, roads and public services. The challenge is creating enough infrastructure to attract industry while ensuring that the city remains economically viable. KAEC therefore represents a different type of megaproject. It is not simply a city. It is an attempt to engineer an entire economic ecosystem around a strategic location on one of the world's most important maritime corridors.
At number 5 is Al Maktoum International Airport, a project designed to transform Dubai's aviation infrastructure on a scale rarely seen before. The approved expansion is planned around a new passenger terminal costing approximately 128 billion dirhams, with an ultimate capacity of up to 260 million passengers per year. The design includes 400 terminal gates and 5 parallel runways. But the real engineering challenge is not the terminal building. It is the airport ecosystem. A major international airport requires runways, taxiways, aircraft stands, baggage systems, security infrastructure, fuel systems, cargo facilities, passenger processing, air traffic systems, roads, rail connections, power generation, and water infrastructure. At this scale, automation becomes essential. Future airports can use biometric identification, automated baggage handling, intelligent passenger flow management, advanced security systems and data-driven operations. The airport is also intended to become a major future hub for Emirates and other carriers. While operations at Dubai International are planned to transition toward Al Maktoum over time, the engineering philosophy is clear. Don't build an airport simply for today's demand. Build an infrastructure platform capable of supporting the aviation network of tomorrow. If delivered at its planned scale, Al Maktoum will be less like a traditional airport and more like a gigantic transportation city.
At number 6 is a project that does something extraordinary. It does not primarily move people, it moves water. China's south-to-north water diversion project is a vast national water infrastructure system designed to transfer water from relatively water-rich regions toward the more water-stressed north. The overall plan uses multiple transfer routes and, when fully developed, is designed to move approximately 44.8 billion cubic meters of water annually. Technically, this requires far more than canals. The system involves reservoirs, pumping stations, tunnels, aqueducts, pipelines, control structures, and water treatment infrastructure. The central engineering challenge is maintaining hydraulic control over enormous distances. Water must move through different elevations and across natural obstacles while maintaining pressure, flow rate, and water quality. Digital monitoring is increasingly important because engineers need continuous information about reservoir levels, flow rates, structural conditions, and water quality. But the project also demonstrates the environmental complexity of megaprojects. Moving water changes regional resource patterns and creates ecological, economic, and social consequences. The lesson is powerful. When infrastructure reaches national scale, engineering decisions become environmental and geopolitical decisions as well. This is not simply a water pipeline, it is a continent-scale hydraulic system.
At number 7 is Nusantara, Indonesia's new national capital being developed in East Kalimantan on the island of Borneo. This is one of the most unusual mega projects on Earth, because the objective is not simply to expand an existing city. The objective is to create a new political and administrative capital. Nusantara is being designed around the concept of a smart, sustainable, and connected city. The official master vision includes extensive green space, digital infrastructure, integrated transportation, and environmentally conscious construction. The engineering challenge begins with the landscape itself. Roads, buildings, drainage, water systems, electrical networks, telecommunications, and public infrastructure must be developed together while managing the surrounding environment. The project is also incorporating smart city technology. In 2026, the Nusantara Capital Authority announced continued development of its smart city blueprint, supported by international technical assistance. Construction is continuing in 2026, with the authority targeting the development of Nusantara as Indonesia's political capital by 2028. But building a city is much more complicated than building buildings. A successful capital must attract residents, businesses, government institutions, transportation networks, and essential services. That makes Nusantara one of the world's largest experiments in planned urban development where architecture, engineering, ecology, and digital technology must operate together.
At number 8 is Jubail 2, an enormous industrial expansion connected to Saudi Arabia's wider Jubail industrial city. Jubail is not simply an industrial estate. It is a large integrated industrial ecosystem containing manufacturing, petrochemical, energy, logistics, utilities, housing, and supporting infrastructure. The wider Jubail industrial city covers approximately 1,016 square kilometers, with its strategic location on the Arabian Gulf providing access to shipping routes, energy resources, and raw materials. The engineering principle behind an industrial megaproject like this is integration. Factories require electricity. Electricity systems require fuel or other energy sources. Industrial plants require water, cooling, transportation, pipelines, waste treatment, and export terminals. Instead of building these systems independently, industrial cities connect them into one coordinated network. This creates what engineers call an industrial ecosystem, where the output of one facility can become the input of another. Future expansion increasingly focuses on advanced manufacturing, energy efficiency, hydrogen-related industries, carbon management technologies, and increasingly automated industrial processes. But the challenges are equally significant. industrial pollution, water consumption, energy demand, logistics, safety, and the need to maintain thousands of kilometers of infrastructure. Jubail demonstrates how the future industrial city may function, not as a collection of isolated factories, but as one giant engineered machine.
At number 9 is California High-Speed Rail, one of the most ambitious transportation infrastructure programs in the United States. The long-term vision is an electrified high-speed railway connecting California's major population centers. The current construction focus is the 171-mile Merced to Bakersfield segment, while the wider system is planned to extend much further. The engineering challenge begins with the track itself. High-speed rail requires extremely precise alignment. Small geometric errors that might be acceptable on conventional railway lines can become major safety and comfort problems at very high speeds. The system therefore combines dedicated guideways, bridges, viaducts, overpasses, stations, electrification, signaling, communications, drainage and sophisticated train control technology. The 2026 business plan states that track installation is beginning in 2026, with testing planned before passenger service on the initial segment targeted for 2033. The system is designed around electrified high-speed trains rather than conventional diesel locomotives. The technological objective is bigger than simply moving trains faster. It is about creating a completely integrated transportation system where trains, electrical infrastructure, signaling, stations, safety systems and regional transportation networks operate together. The project also demonstrates the difficult reality of megaproject engineering. Enormous infrastructure can take decades to plan, finance, construct and integrate.
At number 10 is Dubailand, a gigantic master development in Dubai designed around entertainment, tourism, sports, hospitality, residential communities, and commercial infrastructure. Unlike a conventional building project, Dubailand is a city-scale development. Its planned footprint is approximately 278 square kilometers, divided into multiple themed districts and large-scale developments. That means the engineering challenge is not simply constructing individual attractions. It is creating the roads, utilities, drainage, power networks, water systems, transportation connections, buildings, and public spaces that allow an entire urban ecosystem to function. The project has progressed through multiple phases over the years, with construction activity varying between individual developments. This is an important distinction. Dubailand should not be imagined as one continuous construction site, but as a huge development framework containing many separate projects. Its future technology potential includes automated construction, robotics, digital project management, smart infrastructure, advanced building systems, and large-scale entertainment technology. The real engineering challenge is coordination. Thousands of separate components must eventually operate as one integrated system. Dubailand demonstrates an important principle of modern megaprojects. Sometimes the biggest construction project is not a single structure. It is an entire network of structures designed to function together.